I'll leave you alone if we need to. But
Yeah, okay. So superconductors are materials that, well, they're common materials. Aluminum is one, for instance, that if you cool it down to an extremely low temperature, behaves quite differently than it has what's called a phase transition, like, broadly speaking, the difference between liquid and solid water, but this is a change in more subtle properties. It goes from being a mediocre conductor of electricity to a very good conductor of electricity if you cool it down enough. A superconductor of electricity, perfect conductor. In principle, you can set up currents in a loop of this stuff and they'll last forever. They won't generate heat and dissipate. They don't need a battery, just keep going. Now, a deep characterization of superconductors, which sounds quite different but turns out to be closely related to this property, is that if you try to put a magnetic field into a superconductor, it won't let you. It will set up currents that cancel the magnetic field that you try to impose. And that means that photons, or the things that make magnetic fields, can't penetrate very far into these materials. If you look at the equations that the photons in a superconductor behave, it turns out that instead of being massless particles that can exert influences over long distances, inside a superconductor, photons are massive particles. So they obey the equations of particles that have non-zero mass, which are less beautiful equations, but valid equations that describe how photons behave inside superconductors. Now, in our models of particle physics, we have especially beautiful equations for particles of zero mass. Those have wonderful properties. However, some of the particles we'd like to describe as having zero mass, they don't. But then we remember the superconductors say that, well, inside some kinds of materials, photons have mass. So we say maybe there's something like that going on in space. Maybe we're living in a different kind of superconductor that doesn't make photons have mass, but would make these other particles, the so-called W and Z bosons, have mass. And that idea turns out to be extremely fruitful. It's been used as the basis of what's called the standard model of electroweak interactions with great success since the 1970s, and experimentalists have tried very hard to knock it down. They would get Nobel Prizes if they disproved it, and they haven't. I mean, it's just looked better and better. So this picture for many years was gathering evidence, but there was one key element missing. Yeah. We didn't know what this material, this so-called, what the material was, what the superconductor was made out of. It's not an ordinary superconductor that's made out of electrons and nuclei, clearly. It's something else that fills space. And what was postulated and what made the equations work was something called a Higgs field, which is broadly similar to this quark-antiquark condensate I mentioned to you. And that was used as a concept with great success for many years, but it was only in 2012, I guess, right?
Yeah, July 4, 2012.
Right, so like after almost 50 years of successful use and towers of theory and experiment based on it, that the substance was actually discovered, the so-called Higgs particle. So this was a tremendous triumph of
and I just find it fascinating. It's so fascinating. That's what my new book is about. But no, seriously, because it is not understood. We live in. There's this. It's as explicit as anything you said.
Yes.
There's a Higgs field everywhere. If you want to think of a material, and if that material wasn't there, we wouldn't have mass. And we are literally like beings living in a superconductor would think photons were. So this world of ours is an illusion because of the material we happen to be embedded in.
Well, it's a pretty convincing illusion.
It's a pretty convincing illusion.
I would call it illusion, but the illusion part is the thinking that empty space is empty. It's not empty.
And the thinking that the particles that have mass always do, and it's the natural way of being.
Yes, that's right.
But if you went outside, the ocean, if you were a fish, you'd learn
Yeah,
very
you'd
differently.
You'd learn things that were quite different.
And it's amazing.
If you had enough imagination, you could have anticipated that while you were still in the water.
Yeah,
And
yeah.
that's sort of what we did.
That's exactly what we did.
Right.
Except, yeah, exactly. And we built the Large Hadron Collider to sort of poke out outside the
That's
water a
right.
little bit.
Yes.
And it's really a testament to the best of what it means being human. And